If you look at the absolute darkest, the emptiest patch of the night sky, the standard mathematical models of our universe basically say there shouldn't be anything there.
Right. Not yet, anyway.
Exactly. The universe is supposed to be too young, too chaotic, and just too dispersed for anything massive to have formed in that dark patch. But we just pointed a telescope at it, and what we found was essentially a 5-car cosmic pileup that honestly completely breaks the laws of physics as we understand them.
It really does. I mean, it forces a total reckoning. We are staring at a structure that is so massive and so incredibly early in the timeline of the universe that the foundational models of cosmology simply buckle under its weight.
Welcome to the deep dive. Now, if you're listening to this right now, you are probably the kind of person who likes to stay informed. You know, the person who reads the science articles, who maybe even took a few astronomy courses back in college.
Yeah, you probably have a pretty solid mental map of how the universe works.
Right. Well, today, we are here to tell you that the map you have in your head has been completely rewritten in just the last few years. The universe you thought you knew is gone. And today, you are about to get a masterclass shortcut to understanding exactly how and why this happened.
And the catalyst for all of this, of course, is the James Webb Space Telescope.
Mm-hmm.
But, you know, it's not just the hardware, it's the sheer volume of paradigm-shifting data coming down from it.
Yeah, it's overwhelming.
We've completely moved past the era of just taking breathtaking qualitative pictures of glowing space dust.
Right, and that brings us to the source material for today's deep dive. We are using this incredibly dense, very rigorous academic manifesto as our foundation. It was published in May 2026 by Alejandro Cariatti Martelloni.
Yes.
Now, if you spend any time on YouTube looking up astrophysics, you probably know him from his channel at Satius. He is brilliant at taking these terrifyingly complex physics concepts and translating them for the public.
He really is. But his formal paper, which is titled JWST Hito Cientificos Mayo 2026, is just on another level entirely.
It's massive.
It is the ultimate State of the Union for the James Webb Space Telescope. What Cariatti Martelloni has done in this paper is monumental. He hasn't just listed a bunch of discoveries. He has synthesized years of raw, perplexing, and sometimes totally contradictory data into a cohesive narrative.
He makes it make sense.
Exactly. He shows us exactly how JWST is forcing astrophysics to transition into hardcore quantitative spectroscopy.
And our mission today is to extract the absolute most mind-bending, reality-shifting aha moments from his work. We're not just going to read a list of space facts.
No, we want to explore the mechanics.
Right. We want to understand how JWST is solving ancient mysteries while simultaneously breaking rules we thought were set in stone. Okay, let's unpack this. We have to begin at the absolute beginning.
The very beginning.
Because to understand how JWST is changing things in our own solar system, we first have to understand how it basically took a sledgehammer to the chronological timeline of the universe itself.
We have to talk about the cosmic dawn.
The cosmic dawn.
Yeah, this is the era right after the Big Bang, when the very first stars and galaxies were supposedly just starting to switch on.
And to really grasp why Cariatti Martelloni's paper is causing such a panic in the astrophysics community, we need to talk about the old rule book.
The standard model.
Right, the model that's been the bedrock of cosmology for decades. Let's start with the Lambda cold dark matter model, or Lambda CDM. Because if you are a cosmologist, Lambda CDM is your Bible.
It is. It's the framework for everything.
Yeah.
In the simplest terms, Lambda represents dark energy.
The force accelerating the expansion of the universe.
Exactly. And the cold dark matter part refers to the slow-moving, invisible mass that makes up most of the matter in the universe. But the core prediction of this model, its most fundamental rule for how the universe builds its architecture, is that structure forms bottom up.
Bottom up, let me make sure I'm picturing this right. Bottom up means you start with the tiniest possible ingredients, and over unimaginable stretches of time, they slowly blom together into bigger things.
Precisely. In the Lambda CDM mathematical framework, right after the Big Bang, you had these microscopic fluctuations in the density of dark matter. And they started to clump together.
Okay.
They formed these small, low-mass dark matter halos. Then, over billions of years, These tiny halos gently drifted together, they merged, and they grew into larger and larger structures.
A very slow build.
Very slow. Eventually, normal matter, gas and dust, was pulled into these massive dark matter gravity wells, which ignited the massive galaxies we see today. It's a prolonged, patient, hierarchical process.
It takes billions of years to build a galaxy, let alone a whole cluster of them. That was the absolute rule.
Right.
Enter the Webb quintet.
Right.
Or, as Cariatti and Martelloni catalogs it in the paper, JWST pointed its mirrors into the deep, deep past and found a cluster of 5 massive, tightly bound galaxies.
5 of them.
Yeah. And the kicker is when we're seeing them. The paper notes they're located at a redshift of Z equals 6.71.
Which is astounding.
If you're listening and wondering what redshift actually means in a practical sense, it's basically how astronomers measure deep time.
Yes.
As the universe expands, light traveling through it actually gets stretched out. It physically shifts toward the red end of the electromagnetic spectrum. So the higher the redshift number, the more the light has been stretched and the further back in time we are looking.
Exactly. The redshift is directly tied to the scale factor of the expanding universe. And a redshift of 6.71 means the light from the Webb quintet has been traveling for so long that we are seeing these 5 massive galaxies as they existed just 800 million years after the Big Bang.
800 million years.
Yeah.
I mean, in the lifespan of a 13.8 billion-year-old universe, that is nothing. It's a toddler.
Barely a toddler.
So we have a bottom-up model that says things take billions of years to slowly merge.
Oh.
And then we have the Webb quintet, existing when the universe barely had time to cool down.
It makes no sense under the old rules.
It's like looking at a brand new, supposedly empty cosmic highway that was just paved yesterday and finding a massive 5-car pileup already blocking the lanes. You have to ask, where did all the traffic come from so fast?
Right.
How do 5 massive bodies even find each other in an expanding void, let alone get into a tightly bound gravitational space in just 800 million years?
Well, the underlying math of Lambda CDM just groans under the weight of this discovery. To truly appreciate the headache this causes, we have to look at the mechanical engine of galaxy mergers. We have to look at dynamical friction.
Dynamical friction. Okay, I want to try to visualize this, because when I think of friction, I think of rubbing my hands together to get warm. How does friction exist in the literal vacuum of space?
It's not physical rubbing friction, it's gravitational.
Okay.
Imagine you are walking through a crowded room. As you push your way through the crowd, the people you pass are drawn slightly towards your wake because of your gravitational pull, assuming, for the sake of the analogy, that you have significant gravity.
Right, and pulling people in behind me as I walk past them.
Exactly. This creates a denser cluster of people directly behind you.
Got it.
Now, what does a dense cluster of mass do? It exerts its own gravitational pull. That dense wake of people now pulls backward on you, slowing your forward momentum.
Oh, wow.
In space, when a smaller satellite galaxy moves through the immense invisible dark matter halo of a larger galaxy, it creates a similar wake of dark matter behind it.
So it's leaving a trail of gravity.
Yes. And this wake exerts a backward gravitational pull, bleeding away the satellite galaxy's orbital momentum. It acts like a brake pedal, causing the galaxy to spiral inward, sink toward the center, and eventually merge.
So dynamical friction is essentially the mandatory braking system that forces galaxies to crash into each other, rather than just slingshotting past one another forever.
That is exactly what it is. And the formula for dynamical friction dictates that the rate of this sinking, how hard the brakes are applied, depends heavily on the density of the dark matter halo it's moving through. So for the Webb quintet to have achieved such an advanced state of fusion, with 5 massive bodies piled up so early in time, the dark matter halos back then must have been unfathomably dense.
Just incredibly.
Way steeper and denser than our standard computer simulations of the early universe allow for.
The universe had to be thicker than we thought. And it's not just that these 5 galaxies found each other, it's what they're doing to each other right now in this observation.
The collision itself.
Yeah. The friction and the tidal shocks of this massive 5-way collision are stripping away the angular momentum of their gas clouds. They are bleeding energy.
Constantly.
All this raw material, this cosmic gas, is free falling into the centers of these galaxies. And that leads us to a number in Cariatti Martelloni's paper that made my jaw drop, the star formation rate, or SFR.
The numbers are staggering.
Yeah.
The combined star formation rate of the Webb quintet is measured at roughly 250 solar masses per year.
If you are listening to this, let's put that 250 solar masses into perspective. Our own Milky Way galaxy is a massive, highly mature, very successful spiral galaxy. We have a lot of gas.
Yeah, a huge amount.
But our galaxy creates maybe 1 or 2 new stars a year, the equivalent of 1 or 2 of our suns.
Right.
The Webb quintet is churning out 250 times the mass of our sun every single year. It is a hyper-accelerated runaway factory of stellar birth.
But again, physics demands a mechanical explanation.
Yeah.
How can gas collapse into stars that quickly?
Good question.
Because normally, when gas compresses under gravity, it heats up. And heat creates thermal pressure, which pushes outward.
A tug of war.
Exactly. This creates a fundamental tug of war in every nebula. Gravity wants to crush the cloud into a dense star, but the thermal pressure of the compressing gas wants to blow the cloud apart.
Right. It's like trying to squeeze a balloon. The more you squeeze, the harder the air inside pushes back against your hands.
That's a great way to think of it. And this brings us to a crucial concept. Cariatti Martelloni details extensively the Kennicutt-Schmidt law and something called the Jeans mass.
Okay, so how does a cloud of gas actually win this cosmic tug of war against its own heat to become a star?
The Jeans mass is the critical mathematical threshold. It defines the exact minimum amount of mass a cloud needs so that its internal gravity can finally overpower its internal thermal pressure.
Okay.
If you want to make stars rapidly, like 250 a year, you need to lower that threshold. You need to drop the thermal pressure so gravity can win easily. And how do you lower thermal pressure?
You have to cool the gas down.
You cool it down.
But how do you cool down a massive, violently colliding cloud of gas in the early universe? I mean, there's no space AC.
No, there isn't.
And this is where JWST spectroscopy, not just its pretty pictures, comes in. JWST didn't just see the starlight from the quintet. It analyzed the chemical spectrum and detected massive glowing halos of ionized oxygen surrounding the entire collision.
And oxygen is the key to the whole machine. Yeah. In astrophysics, oxygen is an alpha element. Doesn't exist at the beginning of the universe.
Oh, right, because there was only hydrogen and helium at first?
Exactly. It is synthesized only in the nuclear furnaces of massive, extremely short-lived stars, and it is violently expelled into space when those stars go supernova.
So it's like a secondary product.
Yes. The presence of massive, sprawling oxygen halos this early in the universe is a smoking gun. It proves that a very first generation of massive stars had already lived, died, and exploded, seeding the surrounding gas with heavy elements.
So the first generation lived fast, died young, and flooded the zone with oxygen.
Exactly.
But how does the oxygen make more stars?
Because oxygen is a phenomenal atomic coolant.
Really?
Yeah. When oxygen atoms collide with other particles in a hot gas cloud, they absorb the kinetic energy of the collision. The oxygen atoms' electrons get excited, and then they immediately radiate that energy away into deep space as an infrared photon.
Oh, wow.
It literally bleeds the heat out of the cloud. As the temperature plummets, the thermal pressure drops alongside it.
And so the Jeans mass threshold crashes.
Exactly. Suddenly, immense volumes of gas that were previously stable and pushing outward just instantly collapse under their own weight.
It creates a runaway feedback loop. The galaxies crash, the gas compresses, the first massive stars are born, they explode, their oxygen cools the remaining gas, which lowers the threshold, causing even more gas to collapse into stars instantly.
Boom.
Boom. You get an astronomical star formation rate of 250 solar masses a year. It's a brilliant, beautiful mechanical loop.
It really is.
But this brilliant mechanism creates a massive headache for cosmologists trying to understand the whole universe.
What's fascinating here is how this intensely local pileup of galaxies reverberates across the entire scale of cosmology. It collides head-on with what we call the Hubble tension.
I am so glad you brought this up, because if you haven't been following astrophysics drama, the Hubble tension is arguably the biggest crisis in modern physics.
Without a doubt.
It's a slow-moving train wreck that has been literally causing fights at conferences for a decade.
Yes, it has.
Let's outline the tension. Basically, we have two different ways of measuring how fast the universe is expanding. When we measure the expansion locally, meaning we look at nearby stars, Cepheid variables, recent supernovas, we get a very fast rate of expansion. The universe is flying apart quickly.
That is the late universe measurement.
Right. But when we look at the early universe, specifically the cosmic microwave background, which is the leftover radiation from the Big Bang, and we run that data through our standard Lambda CDM model.
It predicts a significantly slower rate of expansion for today.
Exactly. So the early universe math says the universe should be expanding slowly, but our local eyes see it expanding fast.
And the disagreement between these two measurements has reached a statistical discrepancy of over 5 sigma.
5 sigma.
Yes. In physics, a 5 sigma discrepancy means this is not a rounding error.
Yeah.
It's not a smudge on the telescope lens. It means something is fundamentally wrong or missing in our foundational model of reality.
And the Webb quintet makes this tension worse, right? Because these massive early galaxies act like giant gravitational lenses.
Yes, they do. Their immense gravity physically bends and distorts the light of the cosmic microwave background as it travels past them toward our telescopes.
Okay.
If our standard Lambda CDM models assumed the early universe was empty and didn't account for these massive galaxies existing this early, then our calculations of the background radiation have been systematically biased from the start.
We've been looking through warped glass without realizing the glass was warped.
Precisely.
So how does Cariatti Martelloni's paper suggest we fix the math?
Well, the existence of the quintet forces theorists to look for a mathematical bridge. And the leading candidate right now, heavily fueled by this JWST data, is a concept called early dark energy, or EDE.
Early dark energy. Okay,
Yeah.
we all know about regular dark energy.
Anyway,
That's the mysterious, unseen force that makes up most of the universe and is pushing everything apart right now. What makes early dark energy different?
early dark energy models propose that there wasn't just a slow, constant push. Instead, they theorized there was a temporary, massive injection of a dynamic energy field right before the universe cooled enough to form the first atoms.
Just a sudden burst.
Yes, this specific period is called recombination, occurring around redshift 1100. This temporary burst of energy does something very specific to the math. It mathematically shrinks what we call the sound horizon of the early universe.
The sound horizon. Think of that as the cosmic yardstick we use to measure the bumps and ripples in the cosmic microwave background.
Exactly. If you shrink the yardstick you were using to measure the early universe, the mathematical equations suddenly require a much higher expansion rate today in order to make the numbers balance out.
Oh, I see.
It perfectly bridges the gap between the slow early universe measurements and the fast local measurements. It potentially solves the Hubble tension entirely.
It literally fixes the math glitch.
It does. But more importantly for our discussion of the Webb quintet, this early dark energy model has a side effect. By injecting that energy, it temporarily increases the density of matter clustering.
It supercharges the halos.
Exactly. It acts like a supercharger for dark matter halos. It provides the exact conceptual and mathematical framework needed to rapidly assemble massive, luminous structures like the Webb quintet almost overnight.
It's wild. By proving these early massive galaxies exist, JWST is basically forcing us to accept that the universe had a secret, hidden turbo boost of energy at the very beginning of time that we never knew about.
Yes.
The bottom-up model of slow, patient growth is completely dead.
It's a complete paradigm shift. The universe didn't slowly assemble itself. It snapped together violently and rapidly.
Okay, so if galaxies in the early universe could form impossibly fast, totally defying our old models, we naturally have to ask, does this accelerated massive growth happen on a smaller scale?
Right.
Does it happen to planets too?
And the answer in the report is a resounding yes. And it's forcing us to redefine what the word planet even means.
We are shifting our focus from the macroscopic scale of the cosmic dawn down to the microscopic scale of stellar neighborhoods. And just like with the galaxies, the old definitions are failing us completely. Let's talk about 29 Cygni b.
Yes, 29 Cygni b.
It's an exoplanet located about 133 light-years away from Earth. It orbits its host star at a distance of 16 astronomical units, or AU.
Which is quite far out.
Right. 1 AU is the distance from the Earth to the Sun. So 16 AU puts it roughly where Uranus is in our solar system, out in the cold dark. But 29 Cygni b is not a frozen ice giant like Uranus. It has a staggering, mind-bending mass of 15 Jupiters.
15 Jupiters. And right there, classical astronomical taxonomy hits a brick wall.
Yeah.
For decades, astronomers used a very strict, somewhat arbitrary mass limit to categorize objects in space. The absolute rule of thumb was that 13 Jupiter masses was the ceiling for a planet.
Right. And I have to push back here because this is exactly what I was taught in college. I was taught that 13 Jupiters is the hard limit.
Most people were.
Because if an object gets heavier than 13 Jupiters, its internal gravity generates enough pressure and heat in its core to ignite the nuclear fusion of deuterium.
Yes.
Deuterium being a heavy isotope of hydrogen. And if it burns deuterium, it is officially classified as a brown dwarf, a failed star.
Exactly.
It is not a planet. End of story. That was the rule. So if 29 Cygni b is 15 Jupiter masses, why are we calling it a planet? Why isn't it just a brown dwarf?
That is the exact debate Cariatti Martelloni dismantles in his report. He argues, using JWST's findings, that taxonomy, whether we call an object a planet or a star, should not be based on a lazy, arbitrary mass limit where one specific isotope happens to ignite.
So it's not about the mass.
No, it's not about how heavy it is. It should be based on the thermodynamics of formation.
Okay.
The classification should answer the fundamental question, how is the object born?
The birth story dictates the identity. I like that. Okay, so we have two competing birth stories for massive gas bodies, core accretion versus gravitational instability. Let's break these down because this is where the physics gets really intuitive. I like to think of these two methods in terms of construction.
Okay.
Core accretion is like building a skyscraper floor by floor. It's a bottom-up process.
Right.
You start with a massive disk of microscopic dust. That dust gently clumps into pebbles. The pebbles crash into each other to form boulders. The boulders smash together to form a solid, rocky core.
Which takes time.
Exactly. Once that solid, rocky core gets massive enough, usually a few times the mass of Earth, its gravity becomes so strong it starts vacuuming up all the loose hydrogen and helium gas around it in the protoplanetary disk, slowly building the giant atmosphere of a gas giant.
That's a perfect analogy for core accretion. It's a slow, sequential buildup of solids, followed by a sweep up of gas.
And the other one.
The alternative model, gravitational instability, is a top-down process.
Right. If core accretion is building a skyscraper floor by floor, gravitational instability is like dropping a fully formed giant concrete block from the sky. There's no slow building process. A massive, freezing, cold cloud of gas out in the disk just becomes gravitationally unstable and instantly collapses under its own weight into a giant sphere. There is no rocky core required.
Exactly. And the mathematics that govern whether a disk can undergo this top-down collapse is quantified by something called the Tomb-Q parameter.
Let's unpack the Tomb-Q. If I'm a gas cloud trying to form a planet, what forces are fighting against me?
The Tomb-Q parameter is essentially a structural integrity score for a spinning disk of gas.
Okay.
It's a fraction. In the numerator, you have the forces that want to rip the disk apart.
Which are?
This includes the thermal heat of the gas pushing outward and the sheer kinetic force of the disk's orbital rotation, which wants to fling material away like a merry-go-round.
So heat and spin.
Yes. In the denominator, you have the gravitational force of the mass itself, which wants to pull the gas together.
So it's rotation and heat versus gravity.
Precisely. If the disk is very cold, meaning low thermal pressure, and very dense, meaning high gravity, the Tomb-Q value drops below 1.
And when it drops below 1?
When Q is less than 1, gravity wins decisively. The disk fragments violently, and a massive clump of gas collapses instantly to form a giant body.
So the multi-million-dollar question is, did 29 Cygni B form bottom-up like a skyscraper via core accretion, or top-down like a concrete block via gravitational instability?
Right.
Because for a long time, the scientific consensus was that anything that massive 15 Jupiters had to be formed top-down. The assumption was that core accretion was simply too slow.
Way too slow.
It would take too long to build a rocky core massive enough to sweep up 15 Jupiters worth of gas before the host star's solar winds blew all the gas away.
But JWST proved that assumption entirely wrong.
Completely.
And it did so through direct spectroscopic imaging. The key is in the chemistry.
Okay.
When a gas cloud collapses top-down via gravitational instability, the resulting body is essentially just a concentrated sample of the original nebula it formed from.
Like scooping a cup of water from the ocean?
Exactly. It didn't selectively gather materials.
Yeah.
It just collapsed everything in its immediate area. Therefore, it should have the exact same chemical makeup as its host star.
Which means
It should have very low metal content and be almost entirely hydrogen and helium.
But when JWST looked at the atmospheric spectrum of 29 Cygni B, it found something completely different. It found massive, deep absorption signatures of carbon dioxide and carbon monoxide.
Heavy elements.
Right. By mathematically quantifying these signatures, scientists determined that underneath all that gas, this planet has a solid core made of roughly 150 Earth masses of pure metals. And remember, in astrophysics, a metal just means any element heavier than hydrogen and helium.
150 Earth masses of heavy elements packed into a core. That is an incredibly brutal, hyper-enriched metallicity. It is wildly out of proportion compared to the chemical makeup of its host star.
You simply do not get that kind of targeted chemical enrichment from a top-down collapse. A gas cloud collapsing doesn't magically sort out heavy metals.
No, it doesn't.
The only way to get a core that dense with heavy metals is if you built it piece by piece, bottom up, sweeping up millions of rocky planetesimals. It had to be core accretion.
The evidence is undeniable. 29 Cygni B is a planet. It formed via core accretion, despite being massive enough to burn deuterium.
The 13 Jupiter mass limit is officially obsolete.
It is. But, as with everything in Cariatti Martelloni's paper, solving one mystery creates a new crisis.
Of course it does.
This realization breaks our current hydrodynamic models of how core accretion works.
Why does it break the models?
Because of the location. 29 Cygni B is 16 AU away from its star.
Way out there.
Yeah. To build a solid core of 150 Earth masses that far out, the original protoplanetary disk's isolation mass, which is the maximum theoretical amount of solid material available in that specific orbital zone, must have been unbelievably rich in carbonaceous volatiles.
Okay.
Our current models just don't allow for a stellar disk to be that rich and massive so far from the center.
It's like finding out someone built a 100-story steel skyscraper in a neighborhood where the zoning laws and supply chains say there's only enough steel available to build a 2-story house.
Exactly.
Where did the material come from? We have to completely rewrite the zoning laws of protoplanetary disks.
We do, and JWST isn't just rewriting the rules for distant exotic systems 130 light years away. It's doing it right next door in ways that impact our most fundamental search for life.
Yes, let's bring the focus much closer to home. Let's talk about Alpha Centauri A.
Our closest neighbor.
Just 4 light years away. It's a sun-like star, part of a binary system with Alpha Centauri B. For decades, Alpha Centauri has been the holy grail for exoplanet hunting. I mean, it's right there. But ironically, being so close has made it a nightmare to actually observe.
It really has.
Right.
The core problem is optical contrast. Alpha Centauri A and B are incredibly bright stars, and from our perspective on Earth, they are separated by a minuscule angular distance. Trying to spot the faint, cold thermal glow of a planet orbiting them is literally like trying to spot a firefly buzzing around the blinding beam of a lighthouse, while a second lighthouse is shining directly into your eyes from right next to it.
That's a great visual. The starlight completely washes out the planet.
Washes it out.
But JWST's mid-infrared instrument, known as MRI, managed to pull it off. And it used some absolute optical wizardry called coronography. Specifically, it used a 4-quadrant phase mask and principal component analysis, or PCA.
That's right.
Let's break this down for the listener because it sounds like magic. How exactly does a 4-quadrant phase mask let us see the firefly next to the lighthouse?
At a basic level, a coronagraph physically blocks the blinding light of the star. It's like putting your thumb over the sun so you can see a bird flying by.
Okay.
But the 4-quadrant phase mask is a massive leap beyond a physical blocker. It actually manipulates the wave nature of light itself.
How so?
The mask divides the incoming starlight into 4 sections. It then physically shifts the phase of the light waves in alternating quadrants.
Okay, so it alters the waves.
Exactly. So when the light waves from the star eventually meet at the detector, the peaks of one wave perfectly align with the troughs of another.
Oh, wow.
They destructively interfere with each other. The starlight literally cancels itself out.
It's active noise cancellation like in your headphones, but instead of sound waves, it's doing it to light waves.
Precisely.
Ah.
It creates an artificial deep shadow right where the star is.
That is incredible.
But even with that shadow, there is residual optical noise created by the telescope's own mirrors.
Yeah.
That's where the PCA algorithm, the principal component analysis, comes in.
What does the PCA do?
PCA takes thousands of reference images of other empty stars to build a highly accurate mathematical model of exactly what JWST's specific optical noise looks like. It then systematically subtracts that mathematical noise from the Alpha Centauri image.
And when the math was done and the dust settled, MIRI detected something incredible. It found the distinct thermal signature of a gas giant, roughly the size of Saturn, orbiting Alpha Centauri A at a distance of 2 AU. Yeah. For context, in our solar system, 1 AU is Earth and 1.5 AU is Mars. A 2 AU orbit puts this massive gas giant right on the outer edge of Alpha Centauri A's habitable zone.
Oh, yeah.
The habitable zone being the Goldilocks region where the temperature is just right for liquid water to exist on the surface of a rocky planet.
Yes.
Now, if I'm listening to this, I might think, okay, cool, a giant planet out past Mars. What's the big deal? Can't it just mind its own business while Earth-like planets form closer to the star?
Unfortunately, no. Gravity is an absolute tyrant.
The tyrant.
A Saturn-sized mass moving through a slightly elliptical orbit at 2 AU would exert immense repeated gravitational perturbations on the entire inner system.
Okay.
As it swings around, its gravity would dynamically wreck the orbital resonances of any smaller Earth-like planets trying to coalesce from the dust closer to the star.
It would act like a cosmic wrecking ball.
A wrecking ball, exactly. It just clears out the entire inner system.
It would either fling those smaller rocky planets into the star to burn up, eject them out into deep freezing space, or cause them to smash into each other and shatter.
It is a devastating blow to our hopes for that system.
Yeah.
Finding a massive gas giant in that specific orbit suggests that Alpha Centauri A's habitable zone might not be a cradle for life. It might just be a sterile, chaotic wasteland. A planetary demolition derby overseen by a rogue Saturn.
It's a really sobering realization. We always hoped our closest neighbor would be Earth 2.0, but the architecture of a solar system determines its biological destiny. And Alpha Centauri A's architecture looks incredibly hostile.
Which naturally forces us to shift our perspective. If the mechanical architecture of nearby systems is hostile, we have to look for chemical proof of life elsewhere.
Exactly. We are moving from the mechanical destruction of habitable zones to the chemical hunt for biosignatures. And we absolutely have to start with a very famous, very recent false alarm that Cariatti Martelloni's paper completely deconstructs. Let's talk about the saga of K218b.
It is perhaps one of the most important cautionary tales in modern astronomy.
If you read any science news in 2023 or 2024, you definitely saw the headlines about K218b. It's a sub-Neptune exoplanet located about 120 light years away.
Right.
Researchers analyzed JWST data and claimed it was a Haitian world. Haitian is a portmanteau of hydrogen and ocean.
Yes.
They claimed the entire planet was covered in a global liquid water ocean, trapped under a thick greenhouse-like hydrogen atmosphere. But the real bombshell was that they claimed to have detected dimethyl sulfide, or DMS, in the atmosphere.
And DMS is incredibly significant.
Why?
Because on Earth, dimethyl sulfide is a byproduct of life. It is almost exclusively produced by living organisms, primarily marine phytoplankton in the oceans. It is not easily produced by geological processes.
So when they saw DMS on an ocean world, it was heralded as the first potential biosignature on an exoplanet. The media went wild. We found alien plankton.
We did not.
No, we didn't. It was a beautiful, elegant hypothesis that was entirely wrong.
Completely wrong.
Cariatti Martelloni's 2026 report shatters the Hyson theory using the most rigorous application of Bayesian inference we've ever seen in exoplanetology.
To understand how they proved the biosignature was fake, we have to understand the mechanics of transmission spectroscopy and a concept called atmospheric scale height.
Let's break that down. How do we even know what's in the air of a planet 120 light years away?
We wait for the planet to pass directly in front of its host star, from our perspective.
A transit.
Right. As it transits, a tiny fraction of the starlight filters through the very edges of the planet's atmosphere before reaching JWST.
Okay.
Now, different molecules in the atmosphere like water, methane, or DMS absorb very specific wavelengths of light. When we look at the spectrum of the starlight, we see dark gaps where those specific colors are missing. We measure the size and location of those gaps to identify the chemical composition of the air.
But the visibility of those gaps depends on how puffy the atmosphere is, right?
Precisely. And that puffiness, the atmospheric scale height, is dictated by the mean molecular weight of the gas, which physicists denote with the Greek letter mu.
Ooh. Okay.
This is where the Hyson theory started to unravel. If a planet's atmosphere is made of heavy molecules like water vapor or carbon dioxide, the mean molecular weight is very high. Because the gas is heavy, the planet's gravity pulls it down tightly against the surface.
It compresses it.
Exactly. Yeah. The atmosphere becomes very thin and highly compressed.
And when starlight tries to pass through a tightly compressed atmosphere, it's like trying to shine a flashlight through a brick wall. The absorption signals become very flat, muted, and incredibly hard to read.
Exactly. But K2-18b supposedly had a primordial hydrogen atmosphere. Hydrogen is the lightest element in the universe. It is at very low molecular weight.
So it's not compressed.
No. An atmosphere of mostly hydrogen inflates like a massive hot air balloon. It creates a vast, puffy atmosphere that produces extremely deep, clear, easily readable absorption spikes in the spectrum.
So the original researchers saw these massive spikes in the data and thought, aha, look at these deep signatures. It must be dimethyl sulfide.
Right.
What went wrong? How did they misread the data so badly?
They fell victim to two things: parameter degeneracy and a physical instrument error.
Okay.
In 2025 and 2026, a different team of scientists ran over 250 massive Bayesian retrieval models on the exact same K2-18b data.
Okay, before we get into the weeds of parameter degeneracy, let's ground this for the listener. What is a Bayesian retrieval model? Let's use a real-world analogy.
Sure.
If I'm waiting for a friend at a coffee shop and they're 30 minutes late, my brain automatically runs a primitive Bayesian model. The raw data is my friend is late. My model tries to figure out why.
Okay.
Hypothesis A, they hit traffic. Hypothesis B, they overslept. Hypothesis C, they were abducted by aliens.
Good options.
Right. Now, Bayesian logic uses prior probabilities. Traffic is common, oversleeping happens. Alien abduction requires a massive amount of complex, unproven assumptions.
It does.
So Bayesian evidence mathematically punishes the alien abduction theory because a simpler theory explains the data just as well.
That is exactly how a Bayesian retrieval algorithm works for an exoplanet. It looks at the spectrum data and asks, given the optical data we have, what is the mathematical probability that this specific mix of gases, temperatures, and clouds is the true cause of the signal?
It tests everything.
It tests millions of combinations of atmospheres to find the one model that maximizes the Bayesian evidence, denoted as Z. It mathematically punishes overly complex models like a planet with a liquid ocean, a perfect hydrogen atmosphere, and biological life-producing DMS if a simpler, more common model explains the exact same absorption spikes.
And the simpler model won.
By an absolute landslide.
Wow.
The Bayesian retrievals proved with over 4 sigma statistical confidence that K2-18b is saturated with methane, not water. A methane-rich atmosphere can mimic the signals of a water-rich atmosphere under certain conditions. That's the parameter degeneracy.
It's a confusing overlap.
Yes. But the real nail in the coffin for the alien plankton was tracing the dimethyl sulfide signal back to the MRI detector itself.
Wait. The report says the supposed biosignature was actually a false positive caused by pixel shifts. You mean a physical glitch in the camera?
Yes. The JWST is a marvel, but it is a physical machine operating in the harsh environment of space. Minuscule physical shifts in the spatial matrix of the detector array, combined with inaccurate opacity tables used in the original translation software, created a phantom absorption line right where DMS was supposed to be.
Oh my god. I compare this to taking a photo of the night sky, seeing a weird glowing blur, calling a press conference, and announcing to the world you found a UFO, only to realize an hour later you just had a smudge of thumb grease on your camera lens.
It's exactly like that. The data was corrupted by the instrument.
This is brutal.
It's a harsh lesson in the extreme rigors of spectroscopy.
Yeah.
K218b isn't a thriving, ocean-covered haven for life. It's a dead, abiotic, methane-rich mini-Neptune with no surface ocean at all.
But, this false alarm is actually incredibly productive because it forces us to redirect our search. If exoplanets 120 light years away are too prone to instrument errors, where should we look for life?
The answer the paper points to is much, much closer to home. We need to look at our own solar system, specifically the ice moons.
Saturn's moon Enceladus and Jupiter's moon Europa.
Yes.
This is where the chemistry gets genuinely exciting and where JWST shines. JWST turned its infrared gaze toward Enceladus, where we know massive plumes of water vapor are constantly erupting into space from a subsurface ocean trapped under miles of ice.
Right.
But JWST didn't just confirm there was water, it performed a hardcore geochemical dissection of the vapor in the plume itself.
The report specifically highlights a groundbreaking detection. JWST found specific phase ratios of phosphorus in the water. It detected p-phosphate along with the more common PV phosphate.
Let me stop you there, because to a layperson, that just sounds like a bunch of letters. Why is phosphorus, and specifically K3 phosphate, so important? How do we get from floating space water with some minerals in it to the actual building blocks of life?
Well, the presence of p-phosphate is a biochemical holy grail.
Really?
Yes. Phosphorus is an absolutely essential element for life as we know it. It forms the backbone of DNA and RNA, and it's a key component of ATP, which is the energy currency of cells.
Okay, so we need it.
We absolutely need it. But in the universe, phosphorus is usually locked up tightly in solid rocks as highly insoluble phosphates. It's useless to biology if it's trapped in a rock.
Right.
For life to use it, the phosphorus needs to be dissolved in liquid water. This specific ratio of Pfe to Pfe, detected by JWST, mathematically proves that the water shooting out of Enceladus isn't just surface ice melting from friction.
It proves the water is interacting with the rocky core at the bottom of the ocean.
Yes. It proves there are active, intense chemical reactions happening at the seafloor. Specifically, it points to a geological process called serpentinization.
Serpentinization? That sounds like a spell from a fantasy novel.
It's even better, honestly. It's deep geochemistry.
Break it down.
Serpentinization occurs when liquid water reacts directly with iron-rich silicate rocks at high temperatures, like at a hydrothermal vent on the ocean floor.
Okay.
This violent chemical reaction physically alters the rock into a mineral called serpentine. But more importantly, the reaction releases heat and produces hydrogen gas and other organic compounds.
Interesting.
It creates an incredibly ideal, energy-rich, reducing environment.
And a reducing environment is exactly what astrobiologists believe is necessary to jumpstart biology. It is the exact environment where the very first microbial life on Earth likely originated billions of years ago.
Exactly. JWST hasn't found life, but it has found the smoking gun of active hydrothermal vents on an alien moon in our own solar system. It has verified the kitchen where the ingredients of life are currently being cooked.
And the most practical part of this discovery is how we are using the data right now.
Yes.
JWST's highly precise volumetric measurements of exactly how much ice and gas is in these plumes, are actively being used to calibrate the instruments on the upcoming Europa Clipper mission.
It's fascinating.
The SUDA instrument, the surface dust analyzer on the Clipper probe, is literally having its sensitivity dials tuned right now based on JWST's data, so that when the Clipper arrives at Jupiter in a few years, it will know exactly how to sample this bioessential material as it flies through Europa's plumes.
It is a beautiful synergy. We went from a mathematical false alarm light years away to literally setting the dials for a robotic submarine mission to Jupiter based on concrete chemistry.
It really is. And looking at our own local neighborhood brings us to perhaps some of the most baffling discoveries in the entire paper.
Uranus and Neptune.
Yes. JWST isn't just looking at the tiny ice moons. It is fundamentally rewriting our understanding of the massive ice giants they orbit.
These two planets has always been the neglected stepchildren of the solar system.
They really have. Think about the history here. Voyager 2 flew past Uranus in 1986 and Neptune in 1989. It took some relatively blurry pictures, discovered some moons, and that was mostly it. We haven't been back since.
No, we haven't.
And think about the technology we had in the late 1980s. Looking at those planets with Voyager was like using a disposable digital camera from a cereal box compared to the power of JWST.
That's a very fair comparison. The jump in resolution and spectral capability is astronomical.
Yeah.
JWST just spent 15 continuous hours staring directly at Uranus.
Wow.
It created a full 3D map of its atmosphere using the NIR spec instrument. And what it found is that Uranus's internal thermostat is completely inexplicably broken.
Break down the 3D map for us. Why is it a thermodynamic nightmare?
The 3D map charted the temperature and particle density of the ionosphere and the stratosphere, and it found a bizarre, highly counterintuitive vertical disconnect.
Okay.
The density of ionized particles, the plasma, peaks at an altitude of about 1,000 kilometers up. But the heat profile of the planet peaks incredibly high above that, between 3,000 and 4,000 kilometers.
Wait, if the particles are down low, why is the heat so high up? What is heating the upper atmosphere if there's nothing there?
It has to do with Uranus's completely mangled magnetic field.
Mangled?
Yes. To understand this, contrast it with Earth. Earth's magnetic field is relatively neat. It's a dipole aligned mostly with our north and south poles, and it originates from the center of the planet.
Right, like a standard magnet.
Uranus's magnetic field is a disaster. It is tilted a massive 60 degrees away from its axis of rotation. Even weirder, the center of the magnetic field isn't even in the physical center of the planet. It is severely offset.
Wait, so it's not just tilted. The magnet itself is essentially lopsided inside the planet.
Completely lopsided. Because of this bizarre geometry, as the solar wind from the sun interacts with the spinning magnetic field, it creates an equatorial depletion zone.
A depletion zone.
It's a massive region where the magnetic field essentially sweeps ionic particles away, creating a void. But the most shocking discovery isn't the weird shape of the field. It's the overall energy balance of the entire planet. JWST confirmed definitively that Uranus is suffering from persistent secular radiative cooling, what physicists denote as LRAD.
Secular radiative cooling. Secular in physics meaning a long-term persistent trend. So it's losing heat constantly.
Yes. The energy balance equation for any planet's atmosphere factors in heat entering from the sun, internal heat generated by the planet, heat generated by magnetic auroras, and heat radiated away into space.
Okay.
Since our measurements in the 1990s, Uranus's temperature derivative with respect to time has been persistently negative. It is bleeding heat.
Wow.
It is currently sitting at a freezing 426 Kelvin in its exosphere, and it's dropping.
I compare this to a giant cosmic house in the middle of winter. The sun is shining brightly on the windows, the magnetic auroras are acting like little space heaters inside the living room, but the house is still getting colder and colder every single year.
Yes.
The internal air conditioning, this mysterious LRAD radiative cooling, is somehow overpowering all the heating elements combined, and no one knows who touched the thermostat or why it's cranked so high.
This raises one of the most important unresolved questions in planetary science right now. What is driving this immense, relentless heat loss?
What does the paper say?
Cariatti Martelloni suggests in his paper that it's an endogenous mechanism, meaning it comes from within. He theorizes it is driven by complex, poorly understood hydrocarbon chemistry deep in the atmosphere that acts like a thermal siphon.
Oh, thermal siphon.
These chemicals are absorbing internal heat and venting it into space via infrared radiation much faster than the sun or the auroras can replace it. How long these cooling phases last, or if it's a permanent state of decline, is entirely unknown.
That is wild. And then we turn to Neptune.
Neptune is just as fascinating.
Voyager 2 saw beautiful glowing auroras on Neptune in 1989. But in the decades since, subsequent observations from ground-based telescopes on Earth couldn't really find them. A lot of people thought they had vanished, or that Voyager just got lucky.
They didn't vanish. They just shifted their emission spectrum into the deep infrared, waiting for a telescope powerful enough, like JWST, to see them again.
So JWST points its mid-infrared MRI instrument at Neptune, and bam, the auroras light up the detectors. But they aren't neat little halos like the northern lights on Earth or the rings we see on Jupiter.
Wow. Just like Uranus, Neptune's magnetic field is a structural mess. It's tilted 47 degrees off its rotational axis.
Okay.
So instead of nice, stable polar crowns, the auroras on Neptune trace erratic, chaotic, wildly unpredictable paths across the planet's mid-latitudes as the lopsided magnetic field wobbles during rotation.
And JWST didn't just take a pretty picture of these chaotic auroras, it read the specific chemical signature driving them. Specifically, it mapped the presence of H3 plus S, or the trihydrogen cation.
H3 plus S, yeah.
What exactly is H3 plus, and why does Cariatti Martelloni dedicate so much time to it?
H3 plus is essentially the universal infrared thermostat for gas giants across the cosmos. To understand why it's vital, you have to look at normal molecular hydrogen, H2, which makes up the vast majority of Neptune's atmosphere.
Normal hydrogen.
Right, H2 is perfectly symmetrical. It's just two protons sharing electrons equally. Because it is perfectly symmetrical, it lacks a permanent dipole moment.
And what does that mean in quantum mechanics?
Lacking a dipole moment means the molecule is terrible at interacting with light. It is terrible at emitting or absorbing infrared radiation. Therefore, normal hydrogen cannot cool itself down efficiently. It just holds on to heat.
So you have a planet made of a gas that can't cool off. But then the auroras happen. When the high-energy solar radiation or the magnetic auroral energy smashes into that stubborn hydrogen,
it violently knocks an electron loose, ionizing it to create H2 plus Rd. This ionized molecule is highly reactive, and it quickly collides and reacts with another normal hydrogen molecule to form H3 plus Rd. This new molecule, 3 hydrogen atoms bound together, is asymmetrical. Because of its shape, it has a strong dipole moment.
So it interacts with light.
It is incredibly efficient at vibrating, rotating, and emitting infrared photons. It acts as an atmospheric release valve, suddenly bleeding away the heat built up in the upper atmosphere.
It's the planet's sweating mechanism.
Exactly. By analyzing the spectral emission lines of H3 plus JWST, was able to mathematically deduce not just the total amount of plasma in the atmosphere, but the exact thermodynamic temperature of Neptune's chaotic auroras at different altitudes.
It's just phenomenal. We went from blurry pictures in 1989 to reading the exact temperature of a single type of molecule dictating the weather of a planet billions of miles away.
It's a huge leap.
But we need to tie all of this together. We've looked at ancient galaxies colliding and building stars. We've looked at massive exoplanets defying formation rules. We've looked at ocean moons venting the ingredients for life and ice giants freezing over.
We've covered a lot.
We have to end by asking the fundamental question. Where does the physical material, the heavy metals, the oxygen, the carbon, the dust for all of this actually come from? We are going to look at the very end and the very beginning of a star's life.
We're looking at the eternal cycle of stardust, the recycling of the universe.
Let's start with the end of the line. The exposed skull nebula, scientifically known as PMR1. It's located about 5,000 light years away from us in the Vela constellation.
Right.
And JWST peeled back the layers of this dying star to show us exactly how material is violently returned to the universe.
It is essentially a stellar autopsy. MRI and NIRCam imaged this nebula and found something that totally defied standard geometry.
What did it look like?
It has a bizarre bilobed brain or skull shape. And running right down the middle of this glowing, expanding brain is a stark, vertical, totally dark lane of dust, cutting the nebula entirely in half.
Which is weird, right? Because usually when a star dies and blows off its outer layers into a planetary nebula, it creates a nice, neat, expanding spherical bubble.
An isotropic wind.
Right, an isotropic wind blowing equally in all directions. Why does this specific star look like a split brain?
To understand this shape, we have to understand the history of the star and the mechanics of magnetohydrodynamics, or MHD. The dying central star inside the Skull Nebula is likely a hyper-hot Wolf-Rayet star. It is indeed blowing an incredibly powerful spherical isotropic wind of intense radiation and gas outward. But that new wind isn't expanding into an empty vacuum.
It's hitting something.
Yes, in a previous phase of its death, what astronomers call the asymptotic giant branch, or AGB phase, the star puffed up and blew off a much slower, denser wave of material.
Like an earlier breath.
Exactly. Over thousands of years, because of the star's rotation, its magnetic fields, or perhaps the gravitational influence of an unseen binary companion star orbiting it, this older, slower material settled into a thick, dense wall.
A wall.
A massive torus or donut shape of gas right around the star's equator.
So the star is trying to blow a fast spherical bubble today, but it built a brick wall around its own waist 1,000 years ago.
Exactly. When the new hyperfast Wolf-Rayet stellar wind hits that dense equatorial wall of older gas, it can't push through it. The physics of fluid dynamics dictates that the high-energy wind must take the path of least resistance.
Well, where does it go?
Since the equator is blocked, the wind is forced to shoot out vertically. It evacuates perpendicular to the disk, blasting through the much less dense poles as tightly collimated high-speed jets.
Oh, wow.
This violent vertical evacuation creates the two glowing lobes of the brain, while the dense, unmoving equatorial wall forms the dark split down the middle.
It's a violently beautiful display of physics, but it's also terrifying, especially because this dying star is roughly the same mass as our own sun. We are looking into a crystal ball.
We are. It exposes the lethal, messy agony of stellar death.
But the universe doesn't waste material. Out of that violent death, out of that expelled gas and dust, comes birth.
Yes, and JWST captured the mechanics of that birth with unprecedented clarity in two very specific protoplanetary disks. Tau 042021 and OFF 163131.
These two infant star systems are roughly 450 to 480 light years away. And the reason Cariatti Martelloni focuses so heavily on them in the report is because of their spatial orientation relative to Earth. They are viewed perfectly edge-on.
The edge-on orientation is an astronomical jackpot. Because a protoplanetary disk is essentially a flat pancake of spinning gas and dust surrounding a newly born baby star, usually a T-Tauri star. In most observations, we look down at these disks from above.
Like looking at a record player.
Right. The problem is, the central star is so intensely bright it blinds our telescopes, making it impossible to see the faint dust where planets form. But because we are looking at Tau and OFF exactly from the side right down the edge of the pancake, the thick equatorial dust of the disk physically blocks 99% of the central star's light.
It acts as a natural coronagraph.
It does.
I compared this to standing outside on a blindingly sunny day and holding your hand up to block the sun from your eyes just so you can see a bird flying nearby. The thick disk of dust is nature's hand, blocking the central star so JWST can actually see the delicate, faint structures of planets being born in the outer rings.
And what JWST saw in that protected edge-on view allowed scientists to physically observe for the first time the mathematics of dust settling in action.
Okay, let's unpack dust settling, because this is the crucial missing link. This is how we actually get solid planets out of a swirling cloud of smoke.
A protoplanetary disk is an incredibly chaotic, turbulent, violent place.
Okay.
If you want to form a planet, the heavy, microscopic dust particles in the cloud need to sink down to the very middle of the disk, the midplane, so they are close enough to clump together via static electricity and gravity.
Right.
But they have to fight against the violent kinetic turbulence of the spinning gas, which constantly wants to churn them up and keep them suspended.
It's exactly like trying to get fine sand to settle at the bottom of a boiling pot of water. The sand wants to sink, but the boiling water keeps churning it back to the top.
That is the perfect visualization. In astrophysics, this battle between sinking and churning is quantified by two metrics, the Stokes number and the Shakura-Sunyaev alpha viscosity parameter.
Let's start with the Stokes number.
The Stokes number is a dimensionless value that describes how well a solid particle is coupled to the surrounding gas. A high Stokes number means the particle has grown heavy enough that it ignores the churning gas. A low number means it's light and easily swept along by the turbulence.
And the alpha viscosity parameter.
The alpha parameter mathematically quantifies the overall kinetic turbulence of the disk itself, how hard the water is boiling, in your analogy.
Okay.
What JWST's highly sensitive spectral images validated is that the larger dust particles successfully overcome this alpha turbulence. As they bump into each other and grow, their Stokes number increases.
They get heavier.
They decouple from the gas, fight through the turbulence, and sediment rigidly into a dense, incredibly flat plane right at the equator of the disk.
And why is that settling process so crucial for the existence of planets? What happens if they don't settle?
If the dust didn't settle into a dense, quiet plane, any small clumps of rock that managed to form would just be smashed apart.
Because of the turbulence.
Right. The high-speed, chaotic turbulence of the main gas cloud would cause them to collide at destructive velocities. They would grind each other back into dust. But by settling into a dense, dynamically quiet mid-plane, the rocks are shielded from the storm. They can gently merge into larger planetesimals without shattering.
And JWST didn't just prove this math was right. It literally took a picture of the end result. In the disk of OFF 163131, the astrometric images showed massive, physical, asymmetrical trenches completely swept out of the dust layer.
Those trenches are macroscopic mechanical perturbations.
What does that mean?
We aren't just looking at dust. We are looking at the physical ruts carved out by baby gas giants coalescing, increasing their gravity, and aggressively clearing their orbital paths in real time.
We are literally looking in a cosmic mirror at the geological birth of our own solar system. We are seeing what our home looked like 4.5 billion years ago.
We are. It is the full circle of cosmic evolution, captured by a single observatory, from the death of one star to the turbulent birth of new planets.
It really is breathtaking. To recap the incredible journey guided by Alejandro Cariatti Martelloni's research today, JWST has taken our old, blurry 14th century map of the universe and burned it.
Absolutely burned it.
It has proven that the early universe didn't slowly assemble. It violently crashed together at breakneck speeds, potentially powered by the hidden turbo boost of early dark energy. It has shown us that massive 15 Jupiter-sized exoplanets can form from the bottom up via core accretion, completely defying the old mass limits we learned in school.
Right.
It has reminded us of the brutal, unforgiving rigor of Bayesian math, defeating phantom alien plankton on K2-18b, while simultaneously pinpointing the very real chemical hydrothermal vents of our own ice moons. It has revealed the bizarre, broken magnetic thermostats of our freezing ice giants. And we have watched the literal recycling of stardust from the collimated death jets of the Skull Nebula to the physical trenches being carved by baby planets.
It is a profound testament to human ingenuity. We built a machine specifically to look at the invisible universe, and the invisible universe turned out to be far more complex, more dynamic, and more challenging than we ever dared to theorize.
But before we sign off, I want to leave you, the listener, with one final provocative thought to mull over, something that builds on everything we've talked about today. If JWST is showing us that the universe absolutely does not take its time, if massive early galaxies like the Webb Quintet can assemble almost overnight, and if we can physically see massive planets rapidly carving out trenches in protoplanetary disks.
Then what about life?
Exactly. Maybe our entire chronological timeline for the emergence of life needs to be completely compressed?
That is a profound implication. If the physical architecture forms early, the biological chemistry can start early.
Exactly. If the universe builds its architecture this fast, from top to bottom, perhaps the chemical ingredients for life, the warm little ponds, the serpentinizing hydrothermal vents, the complex organics were circulating billions of years earlier than we ever calculated. Are we sitting here on Earth thinking we are the pinnacle of evolution, actually the late bloomers of the cosmos?
The universe might have been teeming with complex chemistry while our sun was still just cold dust waiting to settle into a midplane.
The ultimate cartographer has redrawn the map, the continents have moved, and the dragons are very real. Thank you for joining us on this deep dive. Stay curious.